Welcome to my friends. Today's lectures we are going to discuss the topic molecular orbital theory. In these topics now we are going to discuss this content as like the examples of heteronuclear diatomic molecules having the nitric oxides molecules and nitrosyl ion molecules. So these two molecules we have C molecular orbital diagrams. So nitric oxide molecules, the molecules is heteronuclear diatomic molecules which is formed by the combination of nitrogen and oxygen atoms, and therefore those molecules of nitric oxides having electronic configuration of these two atoms are, for example, nitrogen, they will have 7 electrons. They can distribute it as 1s2, 2s2, 2p3, and the oxygen atom, they will have 8 electrons, and these 8 electrons can distribute it as 1s2, 2s2, and 2p4. In nitrous oxide molecules, all these 15 electrons can made from this nitrogen and oxygen having 7 and 8. Total 15 electrons can be combined and to get thus nitric oxide molecules. Among these nitrogen and oxygen atom, the oxygen, they will have the more electronegative than nitrogen. In nitric oxide molecules, since nitrogen and oxygen atoms, they have different electronegativity, and therefore their atomic orbitals are not the same energy levels. Like oxygen being more electronegative, its orbitals will be at lower energy levels than corresponding atomic orbitals of the nitrogen, because nitrogen is less electronegative than oxygen. Hence, the 2s and 2p orbitals of the oxygen atoms at lower energy level than the 2s and 2p orbitals of the nitrogen. Atomic orbitals of the nitrogen and oxygen do not contribute equally to the molecular orbitals, and therefore the coefficient of atomic orbitals of oxygen, which are greater for the bonding molecular orbitals and smaller for the antibonding molecular orbitals. Therefore, these linear combination of atomic orbitals in nitric oxide molecule, they can be written as the bonding molecular orbitals are as like the psi b is equal to x of psi n plus y of psi oxygen, and antibonding molecular orbitals are like the y of psi n minus the x of psi oxygen. But this combination is found, that is the y is greater than x. But bonding molecular orbitals will resemble the oxygen atoms is more than those of nitrogen atom, and antibonding resembles the atomic orbitals of nitrogen atom than oxygen. This unequal contribution of nitrogen and oxygen atoms, the molecular orbitals can make the NO molecules polar in nature. Now see these molecular energy level diagrams. We observe that the 1s orbitals of nitrogen and oxygen atoms are not in valence shell electrons. These 1s orbitals of these nitrogen and 1s orbitals of oxygens which are not in the valence shell electrons, their interactions are which very negligible, and they can be considered as the non-bonding orbitals, and therefore total number of valence electrons available in bonding nitric oxide molecules are only 11 electrons. Which is 11? These 2, 4, 7, and it is the 4. So total 11 electrons they will be participate in this forming the molecular orbitals, and these 11 electrons are to be accommodated in the molecular orbitals, and these molecular orbitals energy level diagrams of nitric oxide molecules which is shown is here. These molecular orbital energy level diagrams, the 1s orbitals of both the nitrogen and oxygens which as remaining the non-bonding molecular orbitals. The 2s orbitals of nitrogen, these 2s orbitals of the nitrogen overlap with the 2s orbitals of oxygen atoms and to form sigma bonding and sigma antibonding molecular orbitals. Similarly, the 2p orbitals of the nitrogens overlap with the 2p orbitals of oxygen and to form the sigma and the pi bonding and antibonding molecular orbitals. These out of 11 electrons they can fill up as like the 4 electrons they will get filled as the sigma s orbitals, as like 2 electrons is here and 2 electrons is here. So 2 is a bonding orbitals and 2 is a antibonding molecular orbitals, and remaining 7 electrons means with these 4 and these 3 electrons, total 7 electrons which is remaining, these 6 electrons can fill up to doubly degenerate bonding pi p orbitals like pi p, pi 2px and pi 2p molecular orbitals, and bonding sigma 2pz molecular orbitals, and remaining 1 electrons they can fill up or they can accommodate in the molecular orbitals next higher energy like a pi star 2px molecular energy levels, and this one of the doubly degenerate antibonding pi p orbitals like a pi star 2px, and therefore in nitric oxide molecules there is only a single electrons in antibonding pi star molecular orbitals. Their electronic configuration of nitric oxide molecule can be written as like this kk in a sigma 2s2 sigma star 2s2, then pi 2px2 is equal to pi 2py2 sigma 2pz2 and pi 2px1. So this is the electronic configurations. These electrons 11 can be placed in this molecular orbitals will get permitted by the Pauli exclusive principles and Hund's rule maximum multiplicity, and therefore these molecular structures of nitric oxide molecules can be written as like the nitrogen is equal to 1s2, 2s2, 2p3, and oxygen is equal to 1s2, 2s2, 2p4. And so these atomic orbitals can combine, and to get the new molecular orbitals having the electronic configuration is as like the capital K as a penultimate cell, which is non-bonding, and sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equal to pi 2py2, and antibonding higher energy levels pi star 2px1. Nitric oxide, which is the bond order found to be 2.5, and therefore bond order we can calculate as like the bond order for nitric oxide having the formula is 1 half the n bonding minus n antibonding. Therefore 8 electrons present in bonding and 3 electrons present in non-bonding electrons. Now we have seen let's the how much bonding and how much antibonding molecular orbitals. Now see in molecular orbital diagrams. This is a bonding molecular orbitals. So this is 2, this is 4, 6, and this is 8. So total 8 electrons is in bonding molecular orbitals, and this 2 and 1 of these 3. So this 2 and 1, 3. So 3 electrons in antibonding molecular orbitals. Now we can calculate the bond order for nitric oxide molecules. So 8 minus 3 is equal to 2.5. The bond order of this nitric oxide is less than that of nitrogen and carbon monoxide molecules, and therefore the nitric oxide molecules are unexpectedly stable, having the bond energy is 678 kilojoule per mole. But unusual stability of the nitric oxide molecules can be attributed to rather homogeneous distribution of the charge of unpaired electrons over both the atoms as the electronegativity difference between the nitrogen. Magnetic behavior which shows nitric oxide which has the paramagnetic in nature. Nitric oxide is paramagnetic in nature due to the one of these single unpaired electrons in present pi star 2py molecular orbitals. Now we have see the nitrosyl ion. Nitric oxide molecules can ionize and to get as a nitrosyl ion. That time what happens, the nitrosyl ion has exactly same number of electrons by losing the 1 electrons, as the 14th the nitrogens as like oxygens both will have the same electrons as like the 14. But this electrons is removed during the process of forming this nitrosyl ion leads to strengthening the bond order and by increase the to 3 compared to 2.5 for nitric oxide, the shortening the bond. And we can calculate the bond order for this nitrosyl ion as like 1 half is a bonding minus antibonding is equal to 1 half 8 minus 2 is equal to 3. But nitric oxides which are we have see it is expected to less stable. But due to presence of unpaired electrons in one of the antibonding molecular orbitals, the unusual stability may be due to the charge unpaired electrons being distributed over both the atoms in molecular orbitals. If the electron had been localized one on atom, then molecules would have been unstable. But ionization of nitric oxide by losing these one electrons and to form these nitrosyl ion, the bond order can be increased from this 2.5 to 3, and it leads to strengthening of this bond, and therefore this shrinking the bond length from the value of 1.15 angstrom for nitric oxide to 1.06 angstrom for the nitrosyl ion, and which is quite large, with increase the bond order from 2.5 to 3, and therefore the nitrosyl ions form several nitrosyl compounds such as these nitrosyl bisulfate or this nitrosyl tetrafluoroboron. So these molecules we can form, that is nitrosonium tetrafluoroborate. So these molecules which can forms by nitrosyl ion due to it is more stable. Thank you.